All right, so we're gonna start with sugar, everybody's favorite macromolecule, also known as carbohydrates. Carbohydrates, carbon, hydrogen. That's what sugars are made out of. So we're gonna start first talking about how do we make a polymer? What is a polymer? We'll get into the functions of carbohydrates quick, and then go through three different little types of carbohydrates. And I meant to bring some props, but I didn't bring them, so we're just going to go with what I got here at the desk. Anyway, let's just keep cruising. Okay, so how do we make a polymer? What is a polymer? Polymer. That's the word, right? Polymer. Okay, so poly, this word means many. And mer, you can just think of this as a unit. So it's many units. Polymer, many units. Okay, so what is the opposite of a polymer? Mono means one. A monomer. Mono, this means one. If you have like a stereo and mono, so you're playing both sounds from the same speaker. All sounds are coming through each speaker. That's mono sound. Stereos, you have different sounds coming from each different speaker. And this is, again, a unit. One unit. Okay. Sugar, we all kind of know generally what it is. Before we get into that, let's just kind of talk about monomer and polymer. So there's a couple of reactions that we do to how do we make monomers and polymers. So let's just draw, and we'll just draw them as little circles. And we'll draw our sugars in this purpley color, and we'll fill them in. All right, so we got a monomer of sugar here, and we got another monomer of sugar, let's say. And maybe we got a couple, let's say we got 3. And we're gonna fuse these together, oops, like so. Fuse them together. So these will then become something like this. Whoopsies. Something like this. So then we've got our 3 sugars, and they're now fused together. They're bound to each other. And the way I'm going to represent that is just with a little line between them. And we'll just keep it in the same color, like so. So that's the difference between a monomers, 1, 1, 1, polymer. Now it's 3 in 1, and this would really be an oligomer. Oligo means few, but not going to go into all those details. Okay, so how do we actually do this? How do we actually make monomers and fuse them into a polymer? Well, if we were to zoom way in here on this guy, what it actually looks like is, coming off this molecule, we have an oxygen and a hydrogen sticking off. We have an OH group, a hydroxyl group, if you will. And then over on this side, we got a hydrogen. Okay, and then over here we got a hydroxyl group or an OH sticking off, and over here we got a hydrogen. So what we actually do is, rather than having these oxygens and these hydrogens on here, we get rid of those and we bind them to each other instead. So what happens is we take these off and we fuse these two things together through chemistry. And same thing over here. So what's actually happening is, if we were to just redraw these 3 little circles, let's draw our 3 little circles, boop, boop, beep. Put these in the middle. Redraw our bonds in here, like so. Let me draw them a little fatter. Okay? We've also taken out some water. So we've lost water from each one of these. Yeah, I'll draw it like that and like that. So we've lost H2O. So 2 hydrogens and a oxygen. We've lost H2O. Boom. So we have dehydrated this molecule. We have lost the water. Maybe I'll actually draw them both kind of coming over onto this side over here. Let me get rid of this. Sorry about that. And I'll draw them both kind of coming over here to the side. So we've lost our water. So this is called a dehydration reaction. Dehydration, because we've lost this water. So this is called a dehydration reaction. Dehydration reaction. Because the molecule has lost water. So we take a hydrogen and an OH from each one of the sugars. We pull that out, bind the sugars now to each other. And so we've dehydrated this molecule and gained water through that process. Okay. Now, let's say we take this same molecule. I'm going to take this same molecule and we just kind of reverse it. So we'll take that same molecule and then we'll take our H2Os, H2O, doing some chemistry here, H2O and H2O. And let's say we reverse this. And so now we're going to add water there and we're going to add water there. So we're going to cut this molecule. So I'm going to recopy just the circles here. So these are no longer bound together. So we're going to cut the molecule with water. This would go then here. So we cut the water molecule. Cut the molecule with water. Cut the molecule with water. A word for cutting in biology is lysis. Lysis means cutting. And we cut it with water. This is hydrolysis. Hydrolysis is how you say this, but it's hydrolysis. It's water cutting. It's water cutting equals water cutting. Okay. So a dehydration reaction, let me just write this over here. A dehydration reaction builds polymers. Polymers. Why is that not correct? Polymer. Okay. And then a hydrolysis reaction. Hydrolysis reaction cuts polymers. I don't know why that is spelled wrong. Oh, there's no E at the end because the English language or whatever makes no sense. Let me erase that. That was going to bother me. No, that's not what I wanted. Okay. Sorry, my brain is not working today. Polymers. Okay? Dehydration reaction builds polymers. Hydrolysis reaction cuts polymers. So we add water to cut things. We take water out to build things. This makes sense because in order to connect these carbons, we'd be connecting carbons together. We got to take whatever they're bound to away. And remember, carbon is always bound to a bunch of stuff. But in organic molecules, it's bound to a lot of hydrogen. And in this case, it's also bound to some oxygen. And so we're taking that out, dehydrating the molecule by taking out the water to connect it to those other carbons. And there's specific proteins that are involved in having this happen. If you just left these sugars together, they wouldn't just spontaneously form like this. And I'm just going to briefly talk about enzymes here. I'm actually just going to recopy just this part here, let's say. And we're just going to bring it over here and talk about enzymes quickly. So what is an enzyme? Well, an enzyme is going to speed up this reaction. So it's going to cause this to happen. So let's say this enzyme, it's like this, and it's huge. It's going to come in here, and it's going to like fit these two together, like so. Something like that. And it's going to like chomp down on these guys, blip, and bring these two things together. It's going to change its shape slightly, and it's going to allow this dehydration reaction to occur. And then once it does that, I actually kind of didn't necessarily draw that the best because it would have to fit on here and keep doing this over and over again. Let's say it looks something like that. This also isn't that great. But you get the idea. It's going to have this very specific shape. So an enzyme will have a specific shape to bring two molecules together to speed up a reaction. Speed, edit, boom, bang, speed up a reaction. All right. And it's going to basically increase the amount of dehydration reactions that would occur naturally by like the 50,000, 100 million, quadrillion thousand. It's going to make this go so much faster. And then once it puts these two together, it'll move over here and put these two together, so on and so forth. And it's just going to boom, 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 slide down and create a huge, big old long polymer. Like so. So they have a very specific shape. They bring molecules together. And I can actually, let me just like redraw this out. I want this to make sense. We'll draw it out more simply because I feel like I'm actually doing a very poor job of explaining this. So I apologize for that. Let's kind of just redraw out this same little thing with its two little spots. Oops. Spots for these little circles to fit in here like so. We got our two little circles. Let's see, we got this guy. Bring him over. And we got this guy. And we'll bring him over. Just do these two. That way it's a little simpler. Okay, so these fit in nicely here. I'll make this guy a little bigger. So they fit in there perfectly. Okay. Nice and close. All right. What's going to happen now is now that these are closer, this enzyme is going to basically change its shape. Like so. And it's going to like crunch down on these guys and smush them together. It's going to smush these together. So it's going to crunch down, really bring these closer together. And so I'll just copy this whole thing over like so. And I'll just make this whole thing a little smaller so it crunches it all down a little bit. Yeah, this is working. And so now these are really close. Should have just made these two circles. So now these are just these two circles, and we're going to lose. What are we going to lose here? We're going to lose that water. So that water is going to come out. That H2O is going to come out. Right. And then our product of this reaction. So then we will have our product of the reaction, which is these two circles. Our two monomers are fused together. Like so. Boop. And we still have our enzyme, and it's coming back to this kind of initial state. It's now detached. And we've also got our water, H2O, like so. So the enzyme's not consumed. So the enzyme speeds up the reaction, and the enzyme is not consumed. All right, so that's what an enzyme is. That's how an enzyme works. All right, let me show you a little video of an enzyme. Just kind of going in. I've shown you this one before, but this thing here is an enzyme. It's unzipping these DNA strands. This here is another enzyme, and it's adding more DNA to this strand. So you can see this DNA strand here is single-stranded, and now it's double-stranded here. And so this is like how fast enzymes can work. And look at how crazy and beautiful they are, and look at all these shape changes going on here in this one as it wiggles, and this beautiful, delicate dance, and this is incredible. Every time your cell, any cell in your body divides, it's going through this process of copying its DNA. You were looking at a DNA Xerox machine there. Okay, so that's an enzyme. All right, now let's talk about carbohydrates. This one's going a little long already, and we're only done with the first one. So apologies for all that. Functions of carbohydrates. Okay, what is a carbohydrate? Well, let's talk about its functions, and then I'll give us a little better understanding. Okay, so functions of carbohydrates, and this will be a very fast little portion of this lecture. Number one is energy source. This is where we get most of our energy from. I have a little tea here, and it's got some honey in it. Can't see it, but that is a carbohydrate, right? They taste sweet. They provide us a quick energy source because they're made out of hydrocarbons with a little bit of oxygen. They also are a building material for cells. So they're an energy source, a building material. This is a little aloe vera plant. All of this is made out of a carbohydrate called cellulose. That's what plant cell walls are made out of. Here I've got a little jade plant. Whoop. Right? And it's got a little base, and that little base is made out of wood. Wood is made out of plant cell walls. This is all sugar. This is a polymer, a special polymer of sugar called cellulose. That is sugar. I can't really eat it because I don't have the enzymes to break it down, but termites do. That's just sugar. Your house is built out of sugar. And that sugar came from the air. It's very weird. Okay. So a building material, energy source, energy storage. We use them for energy storage in our liver. Our liver stores over a day's worth of carbohydrates just in the liver alone. And they're used as signaling molecules as well. They decorate our proteins and allow us to recognize self. They allow our immune system to recognize self so that they don't eat themselves. Okay, so those are just some functions of carbohydrates. And let's talk about types of carbohydrates. So we did that. All right, so what is a carbohydrate? I talked about this briefly. C6, we're doing a chemical formula here. C6H12O6. C6H12O6. This is glucose. This is the chemical formula for glucose. And carbohydrates, they always contain this ratio of 1 to 2 to 1. So carbohydrates will contain a 1:2:1 ratio of carbon to hydrogen to oxygen. Pretty nifty. Carbohydrates, 1:2:1. So anytime you see this, C6H12O6, you can know that this is talking about the sugar glucose. And this will come up multiple times throughout the semester. I don't get to talk about plants as much as I want in human biology, but trust me, I will talk about them a little bit. All right, and let's draw a couple of different types of sugars. Well, let's just start with the basic stuff here. What is a monosaccharide? A saccharide is what? It is a single sugar, also known as a simple sugar. Right? A monosaccharide means sugar. This means sugar. And this means one. So one sugar. One sugar, right? So this right here would be a monosaccharide, let's say. And this would be, guessed it, a polysaccharide. So monosaccharide, well, actually, before we get to that, some examples of a monosaccharide would be glucose. Glucose and fructose. All right. Then we got a di. Let's draw it in a different color. We got a disaccharide, which is two sugars connected. All right. An example of this, let's see, is lactose, sucrose, and sucrose. Let's just do those two. So examples of this would be lactose, which is milk sugar. Lactose, which is milk sugar. This is actually made out of glucose. Or, I'm sorry, glucose. Oops. And galactose. And then another example of this is sucrose. Another disaccharide is sucrose, which is table sugar. So this is, if you go into your kitchen and get sugar, it's almost certainly sucrose, and this is made out of glucose and fructose. And these different types of sugars just have slightly different structures. I don't necessarily care that you know what those are, but they're just slightly different little sugars. Just like we have different types of flowers, different types of beetles, different types of trees, we got different types of sugars too. Okay? Monosaccharide, disaccharide, this means a dice, you always have two of those, this means two. And saccharide means sugar. All right, and then we got a polysaccharide. Polysaccharide. This means many sugars connected. Many sugars connected. It's a large molecule of sugars. And a couple examples of these are starch. Actually, let's do it like this. Let's do glycogen, and then we'll do, in plants, we have starch, and we have cellulose. So in humans, we stored this glycogen. It's many, many sugars. It's a big old long chain of sugars. This is in our liver mostly. We can also have this in our muscles as well, in our liver/muscles. Energy storage. And like I said, we have about a day's worth of calories of glycogen within our liver. Pretty cool. Starch, energy storage in plants. So this would be like potatoes, rice, wheat. Those all have starch. And cellulose is building material, plant building material. Pretty nifty there. Okay, plant building material. All right, I've gone on way too long. Let me show you a couple things here, and then we're done. I'll just show you these just so we can see examples here. And then we'll just draw out a single little glucose molecule so you can see what it looks like. So here we've got starch, and here we've got glycogen. You see they're very similar, and we'll be doing this actually in lab. So you can see the way that these sugars are arranged in these little helices, these little spirals, when we get this big long chain of them. Starch makes these beautiful little spirals. Glycogen has a lot of branching. You can have some of these spirals, but they're not as neatly organized. And that's just because these sugar molecules are connected in slightly different ways. That's the difference between starch and glycogen. We just link the sugar molecules in slightly different ways. And one thing is if we take iodine, which is an element, so if you take iodine molecules, like little atoms, like so, and you add them to this, they will fit perfectly in this little spiral. And when they do that, they actually turn blue. It starts to reflect blue light. So iodine, in the presence of starch, turns blue. We're going to be doing that technique in lab this week. Pretty nifty, pretty cool. Okay. Oops, not what I wanted. Not what I wanted. Okay. Let's just draw out one little glucose molecule, and then we'll call it a day. Just so you can see what this actually looks like. So let's draw a glucose just for good measure, so we can know what that looks like. And I'm sorry this is going on so long. All right, we got a glucose molecule. We're going to draw that over here. It is a 6-carbon structure. 5 of the carbons are in the ring and 1 is dangling off the top. So we got it. Looks kind of like this. Right here we've got an oxygen in the ring. Goes down. I'm not drawing this perfectly. This is a little wonky, but that's okay. And then this is a carbon coming up off here. So this would be a carbon, and then it's got a couple of hydrogens coming off of it. It's actually got 2 of them, and then it's also got H2, and it's also got an OH coming off of it. And then over here, we're going to have our hydrogen. We'll have our hydroxyl group. Oxygen's attached there. Here we're going to have kind of the opposite. We're going to have our hydroxyl group up top, and then our hydrogen coming down. And it just kind of flips around here again. Got our hydroxyl group coming off. And then here we got our hydrogen and then our hydroxyl group. Okay, so this is one little sugar. And you can see that if we then, have another one of these, would be glucose. This is where we could pull our hydrogen and our hydroxyl group from to make a dehydration reaction to link these together. And we can link these together in a lot of different ways. Look at all these things dangling off. So this would be a glucose molecule. And let's just count them up. Let's make sure we did this right. So we should have 6 carbons here. 1, 2, 3, 4, 5, 6. Got it. We should have 6 oxygens. 1, 2, 3, 4, 5, 6. Got it. We should have 12 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We're missing 1. Ha ha ha. Look at that. I'm glad I did that. We're missing 1 right there. Isn't that beautiful? C6H12O6. All right, I will C6H12O6 you in the next lecture. Sorry that was long, but it was a little sweet to do.